the derivative. This is not something that we got to discuss when we were doing the cubic function, but it is something that is important in terms of our understanding of how the graph and its first derivative and second derivative are related. Also, they can give us the graph of the second derivative of the third derivative, and then they can ask us questions about the other graphs. So we've got to be able to relate the three to one another. So the best way for me to do this is to use an example, and the one that I'm going to use, I'm sorry, let me just move that over, is this one over here because it's already sketched. Trying to draw these on the board is quite a quite a difficult thing to do. Okay, so let's consider the following graphs. All right, so the first graph that we have is our cubic function. I'm going to highlight that in pink. So this is the graph of f of x. It's the graph x cubed minus 6x squared plus 9x is a cubic function. And this is your cubic function over here. So it's, sorry, I'm just going over the lines here. There's your cubic function in pink. Okay. The graph of the first derivative, I'm going to do in blue. And the graph of the first derivative is a parabola, isn't it? Okay, it is the first derivative of your cubic graph. So that's this one here in blue. There we go. So that's highlighted for you. And then the last one, let's do that in purple. That's the graph of the second derivative. Okay, so the line, the straight line, is the second derivative of the cubic, or it is the derivative of your first derivative. There we go. All right, so there is this graph of the second derivative. Okay, so the pink graph is our cubic function. The blue graph is the graph of our first derivative, and the purple graph is the graph of our second derivative. Now, these are all related to one another in some very interesting ways. Let's start off in the very middle, and let's talk about the point of inflection. Can anybody tell me what the x-coordinate at the point of inflection is in this particular graph? Can anybody tell me, just by looking at the information provided, what is the x-coordinate at the point of inflection? Can anyone see what the x-coordinate at the point of inflection is? Good, well done, guys. Okay, so that's x equals 2. All right, so hopefully that's not too difficult for you to see. What I'm going to do is I'm going to take this pink pen and I'm going to put a pink dot over the point of inflection. So there's your point of inflection. And you're quite right. This is the line x equals 2. Okay, so the point of inflection is at the line x equals 2. So now have a look at the graph of the parabola. What do you notice about x being equal to 2 on the graph of the derivative? What do you notice? So what's the x-coordinate? There we go, Ayanda, at the turning point. So I'm going to put that in blue for you as well. Okay, so on the point, or at the point of inflection, the x-coordinate is the same x-coordinate as the turning point on your parabola. Well done, everybody. What does x equal 2 mean for us when we're looking at the graph of the straight line? So in other words, the second derivative. Not necessarily the midpoint. There we go. That's it. It is the x-intercept. So I'm putting a purple dot over that. Okay, so in other words, what I'm trying to say is the point of inflection, the x-coordinate at the point of inflection, is the same x-coordinate at the turning point on the first derivative is the x-intercept of your second derivative. Is everybody okay with that? Yes, Ayanda, this would always be true. Okay. Sorry, please can we mute? Thank you. So this will always be true. Okay, so for every cubic and its first derivative and its second derivative, the x-coordinate at the point of inflection is the same x-coordinate at the turning point on the parabola is the same as the x-intercept on your second derivative. Okay, now why is this point important to us? It's important to us because when we are looking at the cubic, what is the story when x is smaller than 2? So now speaking specifically about the cubic function, what would we say is happening on the cubic function when x is smaller than 2? So on the cubic, what is happening when x is, sorry, that's greater than, when x is smaller than 2? What's the deal with the cubic function? That's it, Lesedi. The graph is concave down. Very nice, guys. All right, on the cubic function, when x is greater than 2, the graph is concave up. All right, when we are talking about your first derivative, your parabola, what is happening when x is smaller than 2? So looking at the blue graph now, when x is smaller than 2, what's happening? There we go, Kamogelo. It is decreasing. Okay, so when the cubic is concave down, the parabola is decreasing. When x is greater than 2, when the cubic is concave up, the parabola is increasing. The gradient is positive. Okay, now let's have a look at the straight line. What happens when x is smaller than 2? It's below the x-axis where y is negative. Okay, when x is greater than 2, now y is positive. Is everybody happy with that? Are there any questions? Are we all okay? All right, let's go to our turning points. Okay, so Keithlyn, happy. All right, that's fine. So our turning points. So if we go and have a look at our local maximum, all right, which I'm writing here in green. Our local maximum occurs where x is equal to what? On our cubic, our local maximum is where x is equal to? Good, where x is equal to 1. Well done, very nice. What do we notice about the same x-coordinate on the parabola? So where x is equal to 1, what does that represent on the parabola? Okay, that's it. It's one of our x-intercepts. So here we go in orange. Okay, so our local maximum is the same as one of our x-intercepts. Okay, let's have a look at our other turning point, our local minimum. Now, let's just get a different color. Let's go with dark blue. Okay, so here is our local minimum. This occurs where x is equal to 3, and our local minimum is the other x-intercept. They have the same x coordinate. All right, so the local minimum's x coordinate and the other x-intercept are the same. Okay, so these are the things that are important for us when they give us the graph of the derivative and they want us to be able to work backwards. Okay, so we need to know that the x coordinate at the point of inflection is the same as the x coordinate at the turning point on the parabola, the first derivative, which is the same as the x-intercept on the second derivative. We also need to know about our turning points. Okay, the x coordinate at the turning points on our cubic represent or are the same as the x values at our x-intercepts on our first derivative. Okay, so they're going to give you a graph of the first or the second derivative, and then they're going to expect you to be able to work backwards, all right, to your cubic function and answer questions about it based on these relationships. Okay, the other thing that you need to notice at this point, okay, and I'm just going to scooch over and do that on the side over here before we go and have a look at the questions that we're going to answer, is this, okay? If you have a cubic function and your cubic function is concave down, oopsie daisy, and then concave up. Sorry, that wasn't a very nicely sketched cubic function. So that's your cubic function. The graph of your first derivative is always going to be a smiley face. And the graph of the second derivative is always going to be a straight line with a positive gradient. When we are talking about a graph, a cubic function that's first concave up and then concave down, our first derivative is always going to be a sad face parabola. And our second derivative is going to be a straight line, always with a negative gradient. Okay, is everybody happy with that? Right, so the x coordinate at your point of inflection is the same as the x at your turning point on your parabola. Okay, so the x at the point of inflection is the same as the x on your turning point. Okay, this is the same as your x-intercept over here. All right, your turning points, so your maximum and your minimum are your x-intercepts. Okay, so your minimum, your maximum are your x-intercepts. Okay, so now based off of these characteristics, let's go and have a look at an example, and then we're going to work through a slightly more difficult question. Okay, so the first example that we are going to look at is this one over here. Okay, so in the diagram, they have sketched us the graph of the first derivative, a parabola, where f of x is ax cubed plus bx squared plus cx represents a cubic function. The cubic function is not sketched. What is the shape of the cubic function? Use the words concave down and concave up to describe its shape. So I know it's not one of the questions I'm asking you guys. What is the shape of the cubic function? Okay, so first it's concave up, quite right, and then it is concave down. Good. Do you know, good, well done. Do you know the x coordinate at the minimum? What's the x coordinate at the minimum? Yes, you do. What is it, Lesedi? That's it in Kanye, so it's -1. Do you know the x coordinate at the maximum? Yes, you do. It is that's it. It is 5. Good. Well done. Lovely. Excellent. 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 Okay, so the first thing that they ask us to do is they ask us to determine the equation of the first derivative and the second derivative. Good job. How would we find the equation of the first derivative of the graph that's actually in front of us? Any ideas what form I would need to use? Remember, I'm giving you a hint now. You've been given the x-intercepts and one other point, which in this case happens to be the y-intercept. What form? Kamachelo, go for it.
Good evening, ma'am.
Good
I think you
evening.
would, I don't know what they call it, but I would take the exponents and multiply them with the coefficients.
You're right. That would be if you wanted to take the first derivative. Okay. But what
Yes.
I'm asking about is what form of the parabola would we use to find its equation? So if you have a look in Kanyeso and Lesedi have put that form into the chat for us. Well done, both of you. That is absolutely correct. Okay, so we would use y equals a, x minus x1, x minus x2. Very good. Okay. Are you guys, let me give you a little bit of a, well, not much of a challenge. I want you to find the equation of the first derivative. Find the equation of the parabola using this information. And then when you're done, you can say done, and then we'll move on from there. Okay, so this really relates back to everything that we know about the parabola. So find the equation of the parabola. Cool, Lesedi. Lesedi, do you know how to find the equation of the original graph of f? No, you don't. Okay. So Lesedi, just hang tight. And we're going to do it now. I just want to give people a chance to do this one. The others shouldn't be long. In the meantime, Lesedi, why don't you direct message me your answer for the equation of f prime x? The rest of us, are we done? Have we found the equation of the parabola? Anyone got an answer for the equation of the first derivative? Is there anybody that's struggling and doesn't know what to do? So you don't need to get the equation, Kamachelo. The equation's here. You've got to sub into it. So remember, the first thing that you do is you sub in your roots. So that would be plus 1, x minus 5. Then you've got to sub in your other point, which is your y-intercept, 0 and 15. Okay? So when y is equal to 15, x is equal to 0. Okay? So now when y is equal to 15, x is equal to 0. You're going to multiply the brackets together and then by the a. That's going to give you negative 5a. It would be equal to 15, and a would be equal to negative 3. Now you've got to take that and go and sub it back in. So y equals negative 3 into x plus 1 into x minus 5. Leave the negative 3 on the outside. Foil out the brackets. Times through by negative 3. Okay, so there is the graph of the first derivative, or the equation of the graph of the first derivative. Okay, so Olorati, you don't need to get the equation. You need to sub into it. We've got the equation already. Okay, so this is what we've learned in grade 11. When we are given the roots of a parabola and one other point, we have to sub into the equation in that point, in that form. Okay, how did everybody else do? Okay, so Paxton, at the y-intercept. Okay, x is 0 and y is 15. That's the other point that you need to sub in order to be able to solve for a. Katleho, why is there a thumbs down? This is grade 11 functions. This is not matric work. Where's the problem? Your brain is stuck. Oh, shame. Katleho, where did I lose you? Are you sure? Okay. All right. Okay. So I was hoping that by doing this, it would kind of Jude, for the second derivative, that's correct. Yes. All right. Now they also ask us, so we've done this bit over here. We've found the equation of f prime x. Now we need to determine the equation of f of x. So that's our original cubic function. Here's its graph over here on the side. Remember, we drew this there. So now they want us to find its equation. They've given it to us in the form f of x equals ax cubed plus bx squared plus cx. In other words, if they are asking us to determine its equation, they want us to work out the values of a and b and c. Anyone got any idea how we would use the first derivative to be able to do that? How would we use the first derivative to get the equation of the original cubic function? Anyone got any ideas? Well, we know that the first derivative of a cubic is a parabola. So here's the equation of our parabola. So if I take the first derivative here, I would end up with 3ax squared plus 2bx plus c. This term over here, our x squared term, is the same as that. So in other words, what we would do is we would say that 3ax squared is equal to negative 3x squared. Now we're using inspection. Okay, remember we used inspection a while ago to help us solve the equation of a cubic function. So here we're using inspection again. So this means that 3a is equal to negative 3. So a has to be equal to negative 1. The second term of our first derivative is the same as the second term of our first derivative. So in other words, 2bx is the same as 12x. So that means that 2b is equal to 2. So b would be equal to 6. And then we would use the same idea to work out c. Okay, so in other words, let's use a different color. C over here is the same as the third term in our first derivative. Okay, so C would be equal to 15. All right, so that means the equation of our cubic, f of x, is equal to a was negative 1, so that's negative x cubed. B was equal to 6, so that would be 6x squared, and c was equal to 15, so that would be plus 15x. And there's the equation of our cubic. And it makes sense because remember our picture was concave up and then concave down, so we were expecting a negative in front of our x cubed. Any questions? Yeah, you got that. Cool. That's really positive. You were stuck at C, Lorato. Okay, but there we go. Okay, so the first derivative of your cubic is the same as the equation of the parabola. Okay. Okay, it becomes 2bx. Remember, you're using your power rule, Rebetsware. So you're multiplying 2 with the b in front and then taking 1 away from your exponent. Okay, so in Caniso, the reverse of that is called integration, and it's not part of your syllabus. But if you did AP Maths, then they would teach you how to do that. But you're not supposed to use that. Okay, so this is inspection that we're doing here, right? So it's really important, matrix, that you stick to traditional and conservative methods and show as much working as possible. The truth of the situation is we do not know who's marking our work at the end of the year. And sometimes there are people that are employed to mark the matric papers who don't know as much as they should. So rather stick to traditional methods, convention, the stuff that your teacher shows you in class and the stuff that we do here on Watobe. If you start using, the chain rule or all sorts of other things, you might end up in trouble at the end of the year. And I don't want anybody losing marks because of that. Okay. Keithlyn, you'd have to show your working. Okay, so yeah, you'd have to show where it comes from. You'd have to show how you got that A was -1 and B was 6 and C was 15. Okay, rather, if in doubt, rather just show your working. Okay, always a good idea. Okay, so there we've answered the first question. We've got the graph of the derivative and we've got the graph of the original cubic. Now they start asking us questions. For which values of x will the graph of f of x be increasing? Okay, so they're asking us a question about the cubic function. For which values of x is it increasing? So I'm doing it underneath here because we've got our little sketch over there. For which values of x is it increasing? Yes, Kamachelo, but it's between. It's between, not just where x is smaller than 5, but also where x is greater than -1. Okay, so where x is greater than -1, but smaller than 5, our cubic is increasing. There we go, Lesedi, that's it. Okay, so between our turning points. Okay, that's where it's an increasing. Whoopsie daisy, what on earth is that? It's always interesting for me that these graphs end up doing other weird things. Okay, so between there. Good, Sihawu. Okay, for which values of x is it decreasing? For which values of x is it decreasing? Matrix, how would we write that? So it's decreasing here. That's where the gradient is negative. And it's decreasing there. So how would we say that? Good, Lesedi, where x is greater than 5, or? Yes, Lorato, so rather write the x first. So where x is smaller than -1, or where x is greater than 5. That's it. There we go. Kamogelo, I see you got your hand up. Go for it.
I wanted to ask, can you say, can you like exclude where, for example, the bracket that excludes, right? And say from -infinity to, I think, -1. Can you say that?
Absolutely. So Kamogelo, you could also write it like this. So you would say x is an element from round bracket, -infinity to -1 round bracket, union, round bracket, 5, positive infinity, round bracket. Okay, so that's your other option.
Okay, thank you.
No problem. And then this one here as well, if you wanted to write x as an element, round bracket, -1, 5, round bracket, that would be another way of writing that. Okay, so that's not a problem either. Okay, then it says at which values of x will the graph of f have its turning points? Remember, the turning points on the cubic are the same as the x-intercepts on the derivative. Okay, so for part C, this would be where x equals -1, or where x is equal to 5. Okay, yes, that's it, Paxton. -1 or 5. Okay, so those are the basics. Let's go and have a look at another question. Unless there are any last little bits and pieces, if you want to take screenshots, go ahead. Any last questions before we move on? No, we all good? Okay. All right. So let's go and have a look at this question over here. Okay. So again, they give us the graph of the derivative. So they say to us the graphs of y equals f prime x equals ax squared plus bx plus c, and the graph g of x equals 2x minus 4 are sketched below. The graph of y equals f prime x is the derivative of the graph of a cubic function f. The graph of f prime cuts the x-axis at 1 and 3, the y-axis at 0 and 3, B is the x-intercept of G, and C is the turning point of the derivative. The line BC is parallel to the y-axis. The first thing that they want us to do, Matrix, is they want us to write down the coordinates of A. Can anybody tell me what are the coordinates of A? Yes, Nicole, go for it.
The coordinates of A is 0 and -4.
Beautiful. Well done. Very nice. Good job. Okay. Cool bean. And if they want coordinates, let's give them coordinates. We don't want to lose any marks on that. Lovely. Now let's look at question B. Determine the equation of the graph of f prime in the form y equals ax squared plus bx plus c. I'm going to let you guys do that by yourselves. Okay, and then if you've got an answer, you're welcome to share that. Okay, so you guys are doing question B on your own. And you're going to tell me what you've got as an answer. Anyone got an answer to B yet? Done? Me too, Lucedi. Cool, Nicole. Anyone willing to share an answer from the two of you? And Nkaniso, very nice. Good, Sinenhlanhla. Good, Chantal. Okay, so I set it out like this. I just subbed straight in. I worked out the value of A. So that's what I got. There we go. All right, cool beans. Well done. Nice. Question C. Lovely. Well done, everybody. Okay, question C now. Okay, writing down the coordinates of the turning points of f. Okay, so they're talking about the original function. What are the coordinates at the turning points matrix? You can put answers into the chat if you want, or you unmute. What are the x coordinates at the turning points? That's it. Okay, so either x is equal to 1 or x is equal to 3. Remember, the original cubic function would first be concave down and then concave up. Okay, that maximum over there would be at 1. The minimum here would be at 3. Okay, good stuff. Let's have a look at the next question. Determine the values of x for which the graph of f is increasing. Okay, so what would that be? Where is it an increasing function? I'll draw it here again for you guys. Okay, remember our max is at 1. Our local minimum was at 3. So the values of x for which it is increasing, please, matrix. Okay, careful, Kamogelo, between 1 and 3, it is decreasing. Okay, here they wanted increasing first. So for which values of x is it increasing? That's it, Lesedi. So where x is smaller than 1, okay, or where x is greater than 3. Okay, so I just want to go back to something I saw in the chat. Chantel. Oh, okay. All right. You just didn't type the word or. Okay. No problem. You just left out the word or. Okay. But that your answer's not actually wrong, but just don't forget the word or. Okay. Good job. All right. The values of which it is decreasing. This should be easy for you guys now. Where is it decreasing? That's it, Lorato. Good job. So where x is greater than 1, but smaller than 3. Brilliant. Matrix, you are just smashing this. Okay, so we've done where it is decreasing. Now they want the x coordinate at the point of inflection. So there's a very quick and easy way to do this based on the information that we've got. X coordinate at the point of inflection. Can anybody tell me what that would be? X coordinate at the point of inflection. Okay, so Kamogelo, you can only use minus b over 2a. Oh, actually, you're right. If we can actually use that as long as we're working with the graph of the first derivative. That's it. Okay, so we can use, so you can use x equals negative b over 2a if you are working with the graph of the first derivative. If you are working with the graph of the original function, so f, you've got two choices. Either you can use the second derivative or you can use midpoint formula. Okay. Do you want me to show you all 3 ways? Or I don't want to waste your time. Do you want me to show you all 3 different ways? I know some of you got the answer straight away in Kanyiso Klogi. It is x equals 2. Do I need to show you where that comes from? Yes, okay, all right. Okay, all right, cool. Okay, so let's do it this way first of all right? So your graph of the first derivative, remember it's this one over here. Okay, there's your first derivative. Okay, so your first derivative was x squared minus 4x plus 3. So if you do x equals negative b over 2a, you would end up with negative 4 over 2 times 1. So can you see, look there, you would end up with positive 4 over 2, which would give you 2. Okay, so that's one way of being able to do it. Okay, whoopsie. That's one way of being able to do it. Now, if you take your cubic function, okay, the graph of f, do we have its equation? Oh, we don't. Oh, so okay. Oh, sorry. They didn't ask us to get that. Okay. So then the other way that we would do this, all right, is we could use midpoint. Okay, because B is midway between your x-intercepts. So you could do this as well. So you could use midpoint formula. So 1 plus 3 over 2. That would give you 4 over 2, which would be 2. Okay, so that would be the other way of you being able to do it. The second way. If we had the equation of f, we could do it using the second derivative as well. In fact, actually, no, I'm talking nonsense. We can do it that way. We don't need the equation because we've got the equation of the first derivative. Sorry, I'm talking nonsense. Okay, so the second derivative is going to be 2x minus 4. You have to show that at the point of inflection, your concavity is 0. So moving 2x over to the other side, divide both sides by negative 2, x would be equal to 2. Okay, so that would be the other way that you could do this question. All right, so all three methods would be correct. Okay, there you go. So you've got that as well. What? On to the last question. Now, they want us to sketch the graph of f if it is further given that f of 0 equals 0. What are they telling us here, guys? What does f of 0 equals 0 mean? Yes. All right, so that would be an x-intercept and it would be a y-intercept, isn't it? Because at our x-intercepts, y is 0, at our y-intercepts, x is 0. So this over here, they're telling us that the graph goes through the origin. Okay, so we know the graph goes through the other. The second piece of information, f of 1 equals 4 over 3, what does that mean for us? What does f of 1 equals 4 over 3 mean? Okay, so go back and look at this little sketch that I've done for you guys over here. Okay, the little one in purple. Remember, this is our original cubic function here. Okay, so I'm talking here where I'm putting the little purple. So this graph over here. If they tell us f of 1 equals 4 over 3, they are giving us the coordinates at the exactly at the turning point, at the local maximum. Okay, so 1 and 4 over 3 are the coordinates at the local maximum turning point. What does f of 3 equals 0 mean? What does f of 3 equals 0? It's an x-intercept, yes, and it is also the local minimum. Good. Okay, so that means that the coordinates 3 and 0 are, it's an x-intercept, and it is also the local minimum turning point. Good, well done. And what does f of 2 equals 2 over 3 mean? What are they giving us there? That's it, Kamochelo. Okay, so these are the coordinates at the point of inflection. So 2 and 2 over 3 are the coordinates at the point of inflection. Okay, so this is quite a nice question because we're finding the equation of a graph. We are working backwards to the coordinates at the turning points, the values for which it's increasing, decreasing. Okay, the coordinates at the point of inflection. Now they want us to sketch our graph. Well, we've already got a good idea of what it looks like because we did that little sketch up there. So we know that it's concave up and then concave down. Let's just do this, make it just go a little bit further here. Okay. We know that it has an x-intercept at its local minimum. So that means, whoopsie, that's our x-intercept. Well, that's our x-axis. We also know that the graph goes through the origin. So that has to be our y-axis. This point over here, 1 and 4 over 3, and this point here, 2 and 2 over 3, both occur in the first quadrant. Okay, so our local maximum, this is the one that is 1 and 4 over 3. This point over here, our x-intercept, this is at 3 and 0. There's our origin. And our point of inflection is somewhere over there at 2 and 2 over 3. Okay, so we would get probably 3 marks for this graph. 1 for the shape. That means that it is concave down and then concave up. Our second mark is going to be for our turning points. The third mark are for your x and y intercepts. Okay, so that would be how that would be marked.